NIOK, which is the Netherlands Research Institute for Catalysis, Scientific Director of CAT-TIO, which is Catalysis for Sustainable Chemicals from Biomass, elected member of the Netherlands Academy of Technology and Innovation, elected member of the Royal Holland Society of Sciences, alumnus, elected member of the Young Academy of the Royal Dutch Academy of Sciences, elected member of the Royal Dutch Academy of Sciences, elected member of the European Academy of Sciences, author and co-author of 300 refereed papers in international scientific journals. H index is 52 and 100 invited keynotes and plenary lectures at national and international conferences. In addition to that, many awards he got. I think the last one, as I remember, the last one was the award of the International Congress of Catalysis in 2012. It was in Munich this year. So we are completely welcome you to this discussion and to this talk. Looking forward to have. Thank you very much.
Thank you for the very kind introduction. So it's my pleasure to be here. My first time in Saudi Arabia. It's first time in King Abdulaziz University. It's an, as you can imagine, an experience which we enjoy very much. And I would like to thank several people. I think Mohammed, Professor Mokhtar, Professor Al-Kabayi, I pronounce that, Professor Nasser, Sulaiman, Nasser, and Abdullah Abai. I would like to start by saying the following things, is that we are very grateful as Utrecht University to work together with your university in the field of catalysis, and we hope we can establish a strong scientific program with mutual benefit, so we can learn from each other, learn from each other's experience in this, as I will show you, in my opinion, a very exciting and important field of research. So why is it an important field of research? Well, if you think about how we are now doing it in our production of energy and chemicals, materials, and we have to realize that mainly it is based at this moment on fossil fuels. 90% for energy, 10% for materials, and actually the situation is a little bit even less good towards materials and chemicals. About 8 versus 92. And if you think about it, almost all these processes involve, in one or another way, catalysis. So it's enormous. It's a science which really developed over the last century as a very powerful, in order to make sure that crude oil, natural gas, and coal can be converted. Now we know that fossil fuels are limited. They are, or you can say they are limited in their amount. That's true. There's another thing is we will find more and more difficult to access crude oil, coal, and natural gas. And an example can be, for example, when we think about the sands in Canada, where you can extract oil, but at expense you have to put 20, 30, 40 even up to dollars per barrel in it to get it accessible. And the same as you can say about natural gas if you think about the situation in, for example, the Gulf of Mexico or parts of USA where they are now starting huge fracking operations to release out of minerals natural gas which contains even ethylene and then can be cracked. For example, after years of not doing it, also the USA again is building, for example, cracking operations to do this. Now this having said that we still have accessible or more difficult to access natural resources like crude oil, coal and gas, we also have to consider that we want to make more and more a renewable, sustainable approach. It means that we will gradually go from the use of these natural fossil fuels over biomass to, for example, artificial photosynthesis, because sun, we have plenty, and I don't have to tell that in this country, we have here plenty of sun, and that could, if you harvest in an efficient way, to be one of the new ways of getting fuels, which we call then solar fuels. But that is still far away from now. I would say it's still a dream, although people are working on it, and the efficiencies are still low. But people always have to refer to nature. In nature, the efficiency of solar fuel production is also very low. It's also 1% or lower. So in that respect, I think we should not be discouraged because nature is not that yet so efficient. I think we can maybe beat what nature has been developed over the centuries and even millions of years. So we will see a gradual transition, but in all of these developments, Catalysis will play a role. Now, for those who are not less familiar with Catalysis, I have a movie, and this brings you to a petrochemical unit where propane is dehydrogenated to propylene. And this propylene is then converted to polypropylene. And now we jump on a propane molecule, and we will show you what you will see when you go further into this material. So the first thing what you will pass is a kind of bed. Then you will see catalyst pellets, extrudate. These extrudates, they contain crystals, and these crystals, they contain nanopores, and within these nanopores you find balls, nanoparticles, in this case platinum, tin, and they can convert the propane to propylene and hydrogen. So what we'd like to do is we would like to, as I showed you, like a bird zooming in, going into the details and try to uncover what's going on at this active site. So what is the active site? So for this you can make an analogy with this gentleman, which is Hercule Poirot. Hercule Poirot is a Belgian who is a detective, and he likes to find out who is doing the job. In this case, who did it? And for this we need tools, characterization methods. Methods which allow you to characterize catalytic solids while they are working. And this is the field of in situ or operando spectroscopy, a field which my group has been now exploring for some years and trying to push the limits of it. So what you can see is that you have a catalyst, and we would like to take pictures of this catalyst while it's working. So while the cat is doing the job, in this case you see here it's doing a dehydrogenation now from ethylbenzene to styrene, and that can be later on converted to polystyrene. We'd like to know by taking pictures, snapshots, we want to do it. And that is leading to insights, and then you can improve catalyst materials. So what you would like to do is to take not just pictures, but assemble them as a movie, as you can see here. And later on I will show you, I can show you that we are indeed at this moment able to do this. One of the fields which my group is really pushing and trying to get further is what we call the merger between spectroscopy and microscopy. So I would like to focus light towards really like one molecule, as I will show you at the end of my presentation, one particle. And then it's nanoscopy, nanometer scale spectroscopy, or microscopy. It's micrometer scale spectroscopy. And these are the challenges in this field. The challenges are we want to work on 5 dimensions. We want to do it in 3D, X, Y, Z. We want to do it in energy. It means it's like with a rainbow, the spectrum of the light. And we want to do it time resolved. So time resolved, energy resolved, 3D spectroscopy, or you can also call it tomography then. Now why we want to do one particle? I think when we are here in this audience, then you will see that we are all different. So every catalyst particle itself is an individual, which is own performance, own activity, selectivity, and stability. So some is working harder or more efficient and will live longer than the others. You can also see it that way. And that's the same for a catalyst particle. So you will have a Gaussian distribution, and you measure in the end of your reactor just the global activity, but we are interested in the individual, because you can learn a lot by investigating individuals. You can learn a lot about catalysts. So we want to understand distributions in active sites, we want to understand the nature of it, and we want to understand the accessibility. And I will show all these aspects locally during my talk. So we want to understand spatio-temporal heterogeneities. And for doing this is a rather complex slide, but these are the methodologies, all abbreviations, which I will not deal. And here we have the chemical information, so you have high, low. And here you have the spatial resolution, low, high. So what you see is that you want to go in this direction, you want to go to that direction, to that corner. Then you have all the... And these are the materials you can study, and then you can just take this, lay it on top of it, and then you see which method is suitable to study with which methodology. So we call this, as I already mentioned, microspectroscopy, and when we are in the nanoscale, we call it nanospectroscopy, also shortened as nanoscopy. So what are the challenges in this field? And that are the things which I will dwell or I will discuss during my talk. I will talk about single particle detection, single molecule detection, super resolution, 3D staining, integration of spectroscopy with electron and scanning probe methods, and also increasing the knowledge at the solid-liquid interface and surface specificity. I would not have the time to talk about all these in details, and my talk is more meant as a kind of overview what nowadays is possible, where are the frontiers. So I will try to bring that to your attention. Now first we'll start with two trends in this area. So I will talk about what you can do with X-ray microscopy. Most of you are familiar with electron microscopy. You can also use X-rays. What can you do for tomography, nanoscopy with X-rays? I will show in a minute. Another thing is to try to measure vibrational spectra at the nanoscale. And then I will introduce to you what we call tip-enhanced Raman spectroscopy. So let's first start with X-ray nanoscopy. For this I would like to thank the people involved. So the two people mainly doing the work is Ines Dasil Gonzalez Jimenez and Cornel Katz. And I would like to also thank this funding organization and the people on the right. We have been doing this kind of work at Stanford in the USA, the Stanford Synchrotron Radiation Facility, where we have been working up for some period. And this allows you to focus, and that's the crux. The crux of this experiment is to have a zone plate. This is the heart of the device. So X-rays are going to a triple zone plate, a stacked zone plate. And what it's doing is that these X-rays, they will go through this zone plate and will be focused down to something like 15 nanometers. So that means you can then do scanning it at 50 nanometer with X-rays. It's not the same spatial resolution as with electron microscopes, I agree, but now you can do several other things with this kind of, because you can do spectroscopy. Now this kind of setup we have been making ready for catalytic experiments. And so we have been building up an in situ cell, a device, together with gas delivery, mass flow control system, and also a mass spec, which allows you to put a catalyst particle in this cell, bringing a gas through it, measuring at the end conversion, and by the same time measuring then X-ray spectroscopy. And this is shown here in this setup, and the heart of the device is this. This is the heart of the device where you have the cell, X-rays going through, and here you can put on top of it a furnace, and then get in, get out, and you can measure. Just to zoom in, this is on the left the heart of the device, and on the right you see a capillary which is positioned in between the holders where you can bring in gas. I can tell you it is far from trivial to make and make it work, so it's often fails. So now what can we do? Because I just say we have a device, a particle is there, and I have X-ray. So what kind of spectroscopy can we do? So X-ray spectroscopy allows you to probe excitations within a transition metal ion. So you can tell something about its oxidation state and its environment locally. So here I show you that we can measure X, Y maps as a function of energy. Remember the rainbow which I showed. So you have different energy, and we measure at every energy a 2D map. What we then can do is, we can have not only then it's at one energy, but you can also measure the different energies and go through it. And then you have a spectrum. So you have a spectrum, and that is very essential. You have at 15 nanometers a single X-ray spectrum. So a characteristic of its oxidation state. And this we can do then rotation-wise. So we rotate the cell. We have the X-ray going through it, and we scan. And then for every energy and every time is done. So this allows you now to obtain information. And I will show you right away, we applied it on a topic which is on a catalyst material which is very hot at this moment, is Fischer-Tropsch catalysis. It's an old topic, I fully agree on it, but nowadays, for example, in a neighboring country here, it's implemented to try to harvest the natural gas which is converted to syngas, and then you can have it converted to, in this case, waxes, which you crack then to diesel. And for example, there are two major companies who have been investing in this area. The first is Shell, and you have seen that Shell is sponsoring this research, and the other is Sasol, which is a South African company, which is also investing in Fischer-Tropsch systems. And then you can already think that you can not only make diesel, you can also make olefins, you also can make alcohols. And that is where we are interested in. So here I show you a snapshot, a movie, a tomographic reconstruction of one Fischer-Tropsch particle under reaction conditions. So here you see the red is iron, yellowish is titanium, and green is zinc. This particle itself is about 20-30 micrometers, the particle itself. And now I show you the different elements. So this is titanium and zinc only. Zinc, red is the iron. And now we will go through it. We will now reconstruct, and I will show you, I will isolate the volume within this particle. And then you can also access, for example, porosity. Now we go through it and you see holes in the material appearing. So you have morphological information at the nanoscale and chemical information at the nanoscale. And its chemical information, for example, is shown here when we do Fischer-Tropsch. And here you see what is happening when the catalyst is exposed to CO and hydrogen at 350 degrees C. You see the gradual formation or reduction of the iron towards its carbidic form in this material. So this is a kind of showcase what nowadays is on the frontier of X-ray microscopy for catalysis research. The second example is I want to show you how Raman spectroscopy, a vibrational metal, non-metal object, can be met. The two persons I have to acknowledge is Claire Harvey and Evelyn Van-Schooyen-Ten-Lampen, two PhD students in my group, and I also have to thank the two sponsors on the top of this slide. Surface-enhanced Raman spectroscopy. First of all, for those who are not so familiar with Raman spectroscopy is the counterpart of infrared spectroscopy, which is very well known to everyone. Infrared uses the infrared light to make excitation between vibrational levels, the vibrations of molecules. Raman is doing it another way. You excite it with laser light, and then in its process it will not fall back to its original state, and that difference is related to its vibrational levels. There is something what we call surface-enhanced Raman spectroscopy. It means when a molecule is placed on a roughened metal surface, and especially then on silver, copper, what you can have is that when you then shine light on it, laser light, literally here, the molecules which are absorbed here, that signal will be enhanced. And this kind of principle we can now start using. And I first want to introduce you a reaction. You don't have to remember very well what it is. The most important to remember that this molecule has an NO2 at the end. And then here, what you do is you couple it, and then you make this kind of functionality. So what is the experiment all about? The experiment is as follows. We put this molecule with its NO2 on a gold plate with its sulfur groups, thiol groups. What you then do is you excite it with laser light through it, and then you have here a tip. And this tip is what I explained. It's not anymore this surface, but this is, now you can put it as like this. This is the tip. So what you do is you shine. Here you have your gold plated thing. You shine on it, and then at that moment you enhance locally your signal. So that would mean that we should be able now to do this. Well, here I show you the setup, so it's more difficult than I showed with these things. Just to show you what it is all about, here you see the sharp tip, and when you shine here light on it. Now I first want to show you that we indeed are able to measure at the nanoscale molecules. So the first experiment I want to do is just to take the starting molecule, and as you can see we can measure a vibrational spectrum, although it's noisy, but you have to remember we recently found out that the resolution of this method is 2 nanometers, and you measure in total about 50 molecules. So this is a vibrational spectrum of only 50 molecules, which is already an achievement on its own, and later on we'll show you spectroscopy on even 1 molecule. Now to show that we can indeed follow this process, I show you here the beginning, then later on you will see that the process starts and something will change. So now we see a shift, and now we see reactions going on with about 15 molecules only, which are converted from reagent to reaction product. So, now you can say, fine, what can we now learn from? I will now try to illustrate this approach by using the following showcases. The first is I would like to show you how we can image Brunson acid sites in a solid. And we will talk about zeolite materials. And the last part I would like to deal with is catalyst deactivation by coke formation, a process which is notorious in the catalyst field, which makes it that not all our hydrocarbons are converted to the products you want. So let's start with chemical mapping of Brent acid sites. And I will start with model systems first. These are the people I have to acknowledge. PhD student Marianne Cox, Lukas Karwatski, and David Moret, and postdoc Elie Savitsky, all the people on the right as well as the left. I would like to start with explaining the chemistry of what I call a single zeolite crystal. And this is a crystal which is about 100 micrometers in size, and we can now do very nice chemistry, catalytic chemistry on this. Very important is we can map, for those who are not familiar with zeolites, zeolites are crystalline aluminosilicates, which have a three-dimensional structure. You can call it, for those who are familiar with Swiss cheese, so this is a kind of Swiss cheese with the pores of nanometer dimensions. Also, Dutch cheese has this kind of pores. Now, and I think it's very fair, I'm here in a building which has some relation to medical sciences, as I understood. And in the field of medical sciences, and as most probably some of you have been doing that during their education, what you can do is you have a cell, and you can take a dye, and so you can color the nucleus, the cell membrane, and things like that, the ribosomes, and you can make them visual, to visualize. So what we would like to do is, can we now visualize acid sites in that catalyst material? So for this we use a staining reaction, as the same as with your in the medical field where you have a certain dye. Here also you will like, but you want to have a dye you catalytically make. So the dye which we make is, we have styrene, methoxystyrene, which we protonate by the acid site. It reacts with another styrene and it makes this molecule. Now this molecule, for those who have photochemical background, they will right away see it as a conjugated system. So it has a color. And indeed, this crystal, they light up, as you can see, from translucent, they get their color. And for those who are sitting in the front, they really see that here on the edges, the color is different than in the middle. It's much more purple, pink light than blue in the middle. So why? Why the edges are differently colored? Question mark. So let's now first see, when you have a color, that means you can do spectroscopy. So we have in our lab a UV vis microscope, and it allows you to measure spectra, and the spectra only. That's important to realize. I just want to we call this the body, and this is the edge. So that's important to recall. Now you see the spectra for the edge and the body, and you clearly see differences occurring. And this shoulder here, you see, it has to do with this different species you make. So what you have is, different species are formed at different places in the crystal. We call that intraparticle heterogeneities. It's not only that between you and me we have differences, but also within my body, some parts are more active than others. And at this moment, hopefully, my brain is a little bit more active than other parts. So you see that it's reflected in this catalysis. Now on top of it, you can do polarization-dependent experiments. So remember, if you have a camera, you can have a polarizer, and with this kind of weather, you really want to have a polarizer to have certain polarized light only reaching the detector quote of your camera. So the same here. If you do this, you have polarized light. What you have is, this is the crystal. You turn it in this direction, you turn it in this direction. You can make from a colored crystal a translucent crystal. Why? Because in this crystal, the pores of the zeolite, the cheese pores, are oriented in a certain manner, and the molecules are aligned in these pores. Now you can do fluorescence microscopy, and then you can even show that they are present in certain parts. And here you can see from the side, and the coloration means more fluorescent. You see here on the tip already different behavior, and then you somehow see it differently positioned. So somehow, although it looks like a very nice crystal, some parts are more active than others, more parts are more accessible than others. So it's not at all a uniform material. So it's not that between us it's not the same, but also in my body or in the catalyst material there are many differences. So this leads to what we call intergrowth structures of zeolite materials. Now this is the proposal that you have components where the straight pores are oriented in this direction, and here on the edge the straight pores oriented in this direction. How do I know this? Why you believe me, hopefully. But for this we did a very extensive study, because now I'm going back to almost a very long discussion in the zeolite history, since the first synthesis of ZM5 as an important catalyst material in the 70s. Almost everyone had been disputing the intergrowth structure of zeolite ZM5. So we thought, let's now take a whole range of crystals, as you can see here, from different places on Earth, make in different labs. From the one which I already discussed, you've seen it before, up to, and you see it's a very nice cube. You can see that you can have them very elongated, you can just make them almost like a cube. And then you have different forms. So we analyzed them in great detail. And one of the things we have at Utrecht is what we call an EBSD, and what you can do is, it's electron backscattering diffraction. So diffraction by electrons. And this is a very powerful method, because now you can do very funny things. You can measure locally diffraction patterns. And you know the structure of ZM5 from databases. So you can now say, where are my straight pores disoriented at a position, or disoriented at a position, depending on its position in the crystal. And that's what we did. So we know now that indeed the straight pores are there, indeed the sinusoidal pores are there, and they're straight. And now someone can argue, I would ask it if I would be you, Bert, that's fine, but you only analyze the surface. So what is happening inside? So for this we can use what we call gallium ion beam milling. So what you do is you sputter your surface and you start to go inside the material. So what we do is we take a crystal, it's almost like a skyscraper, you cut it off, and you analyze again the diffraction pattern, and then you can again prove that it is indeed the case. So this we apply to all these crystals. And here I show you the four main structures. And this led to what I would call this kind of approach, where we have, for different crystals, different intergrowth structures. So this is the classical model and solves the dispute in literature on how the intergrowth is. Now you can ask you, that what is the relevance for this? Remember that in catalysis is only relevant if my molecule can reach my active site. So if I have diffusion barriers, blockages, I'm not able to reach my active site, and although it can be pretty active, it's doing nothing, because my molecule cannot reach it. And that is the whole point. You can also say it as follows. See, this is the structure of these things. So you have straight pores. Straight pores. So the molecules have to go through this. And then even start to be more complex, because you have even that they can be a little bit shifted. So if these are my straight pores, and these are my straight pores, if a molecule comes from here, and it's a little bit shifted, you see what happens? The molecule is stuck over. So molecules cannot just travel through the material. In other words, and that's the message I want to give with it, although you have a pretty nice crystal, full of active sites, maybe only the outer surface is doing something, but the inner parts of the crystal will never be seen by the molecule. So it's obsolete for its use then. Good. Now you can say, these big crystals, what is now the relevance of them? Let's now go to real catalysts. And the real catalysts which we will discuss are fluid catalytic cracking catalysts, used for cracking crude oil or the heavy fractions of crude oil into gasoline molecules and propylene. And these are the people I have to acknowledge. PhD student Inge Buurman, postdoc here in the group, present today, Javier Ruiz Martinez and Matja Karaman, also PhD student. I have to thank these people for funding, and also the people on the right for the cracks. So those who are not familiar with this process, here's the truck, just to show you the scale that it starts already. So it's a huge operation. The second thing is, here you see the reactor, and this is the regenerator. So it's a huge infrastructure, and here you recover. Now what's happening is you're mixing your crude oil with a huge amount of catalyst material, and on a daily basis it's easily, and I think even here in this country they are building now even maybe the largest SC units ever. But on average, every day about 10 tons of catalyst is just brought into the system. 10 tons new catalyst material. What is this catalyst looking like? These are balls, this kind of balls of about 70 micrometers. And they are not just uniform, they contain zeolites, these crystals I showed you before, but a bit small, together with a lot of other material. So now we say, I show you that we can stain catalyst. Can we now stain this material, this industrial material, and show where the zeolite is, where is the active component? Question. We use the staining reaction, I will not dwell in detail on it. We can do UV vis microscope, we can do certain characterization, and now I come to the real experiment. So we use the reaction in which thiophene is oligomerized, giving rise to this kind of green dots. And now I will show you that we indeed can bring and make this visual. So here on top of it, I show you the ball, and the green spots are the zeolites. So you can really selectively, as with a cell, we can now in 3 dimensions just localize where the zeolite, the active component, is within this material. Now you can say, fine, you showed it. What can we do now with it? For this we work together, as I showed you, with the company Albemarle Catalyst, and they are a producer of FCC catalysts. And we have access to a wide range of materials which are deactivating according to industrial protocols, which we call steam deactivation, cyclic deactivation, and Mitchell steam deactivation. Can we now show that indeed our method works? Because then we should see a decreasing contribution of our zeolite. And it is indeed the case. This is the fresh, steamed, CD and Mitchell deactivated. So here you see how the color is fading away when the deactivation proceeds. You can do statistics on this, and you see that you can then have numbers. And then we got a very interesting sample. We had ECATs, equilibrium cats. They come from a refinery. So we have many refinery ECATs. We just stain them and look for their zeolite acidity. And this is, for example, how the acidity of one of these catalyst materials. So that means that we are now able, with such a sample, as I said, we are all different. So you're an ECAT, we are all, assume we are all ECAT particles, but we have an age distribution. One is a bit younger, the other is a bit older. The one is more active, the other is less active. And so what you can do is we have, like, every particle we can put an activity on. And that seems to be correlating with real catalyst activity. Good. Second example, I want to talk about deactivation, co-formation. And for this, I would like to thank the 2 people involved, David and Eddie Savitsky. David was a PhD student in the group, and Eddie was a postdoc in the group. And we will talk on a topic which we are working together actually with your university. It's on the methanol to hydrocarbon process, and what we have been doing is we have been using again these big zeolite crystals. Now these big zeolite crystals, you can ask yourself, are there good models to study methanol to hydrocarbon process? And the first thing is, just test them. So what we did is, here we have the big zeolite crystals, and this is the conversion as function of time, and this is an industrial sample, a small sample. So these are large crystals, small crystals. Now you see that the small crystals, the industrial sample, has a very high activity in the beginning, but steeply drops within a rather short time. Now, with these large crystals, you see time on stream, very long time, they are active, they are less active, but you can pursue for a while. So that means they are ideally suited, actually somehow answers one of the questions yesterday, what the purpose can be of these model systems. It ideally suits them to do this kind of approach. Now, the first thing is, let's take now these crystals. Remember, I showed these same crystals in this coloration with the blue and the purple. This integral structure, and some parts are more exceptional than others. And this is completely shown in this slide. You see that you have more coke on the tip, on the edge of the crystal versus the main. And we know already now from my explanation before why that is happening. So we can do spectroscopy, and we can now start to measure this browning reaction in the crystal. And this is the spectroscopic evidence for this. Now this is a rather busy slide, and I have to explain it very well to understand the next experiment. And it's as follows. Remember the polarized. Polarized light you can turn. Remember that the crystals have certain parts where the straight ports were oriented in a certain direction. So if the polarizer is in this way, or in this way, it will matter for the absorption. So it's in this way, or in this way. So, what we make is, we make different bands, different degrees of oligomerization, coke degree, and they are preferentially in the straight pores of this material. And straight pores are, if this is crystal, straight pores are like this. So you start to build coke, and the idea which we have, and I will prove it later on, the coke is then grown towards the outside, makes a kind of coat, and then blocks all the pores. So it's from inside, internal coke pushes out, becomes outer, and that is, how can we prove this? We can prove this with our microscopic approach. We have different absorption bands. We can now, with confocal fluorescence microscopy, see the signature of these things, and we can determine who is where. And then we see as function of time. In the beginning we see only these things, and then later on we see a coating form outside. Now you can ask yourself, Bert, but these are big zeolite crystals. Now, can we transfer this to the small scale? And I have to thank Luis Aramburo for us, who will soon finish his PhD. Back to X-ray microscopy, where I started with. I showed you X-ray microscopy. You can do also X-ray microscopy on zeolite and measure aluminium and even carbon. So we can now measure carbon deposits. For this we had, and we developed a few years ago, in situ cell for soft X-ray microscopy. So the X-rays are going through it, the cell, and you analyze it. When we apply this, and we have two catalysts, a catalyst which is steamed and which is parent. The parent catalyst, you have conversion and it drops. And the steamed, it continues. Why this difference? do with that coating. Because I told you that when you make a coating, after a while the coating is there, the molecules cannot enter anymore, and the game is over. So you have accessibility, but now the accessibility is like you have a guard at the gate. You say, don't enter, cool. So we can do this. We can measure X-ray microscopy, and here I show you the coating. These are the spectra, the carbon spectra, and here I show you the catalyst which is going on, continue to work. And this is a picture of the catalyst which deactivates fast, and after a while that red is a coat. It's a coat around the crystal. So we can now understand at the local level why things are deactivating, why things are, for example, working better or worse. I started this presentation with all these methods, and I hope, well, it is an illusion that I can explain all these methods in a talk like this, and I hope I've convinced you that there is a whole zoo, a lot of methodologies, physical-chemical methods available to really start to understand the intricate chemistry, the real detailed chemistry within catalytic salts. I think it's a vibrant field of catalysis where a lot of things have to be done. And I showed you this. But where are we going? I showed you the dimensions, tomography. I showed you X, Y, Z, spectroscopy. I showed you the rainbow. I showed you also a little bit the time frame. But honestly, you were not I didn't show you bond breaking, bond making. I only showed you gradual process, minutes, seconds, whatever. So there's still a way to go. So what are the future developments? I think there is no doubt that we will have to push the time. So it's like with your camera. I think the analogy with a photo camera is very important. It's like, how many shots can you make after each other? And if you can make a lot of shots after each other, you can reconstruct a movie. And then you can see a bond is elongated, broken, another one is made, new molecule is created. We are not yet there. I didn't show you that. What I will show you instead is, I will show you spectroscopy of one more in a catalytic salt. And for this we turn again to these big zeolite crystals. And what we do is, we take our big zeolite crystal, we have a molecule, sulfuryl alcohol, and when it reacts with an acid site, so we do now single acid site, single molecule conversion. So, here I show you something, and I will explain what it is. For those in the front, they should see blinking. And here you see LED blinking, and there you see no blinking. Do you agree? Back to this slide. What do I show you? What I show you is sulfuryl alcohol. It's converted, self-condensed with another one. Your laser light used in the fluorescence microscope detects this first molecule which is created, bleaches away. Show it as a light flash. Now, you can do that in the crystal. You can do that at the surface, a little bit deeper, a little bit deeper. Remember, I told you, these crystals, maybe only the outer surface or the outer layers of the crystals are working. And the deeper layers, they don't work because the molecules do not reach it. So, this is the explanation for this movie now. Because this is the surface, this is 2-3 micrometer deep, this is 6-7 micrometer deep. So at the surface, a lot of conversions, a little bit deeper, still conversions, deeper, that, no activity measured. Just to prove this, the first crystal is a parent crystal. Then we tweak it and make it more active. And then we tweak it and then we deactivate it. So we should be able to see that. So this, here I show you the material which works very well. And this is the material, this is the material which works well. And this is the dead material. You see a lot of flashes on the top. This is at the surface, a little bit deeper, very deep. You see, a lot of activities, even now in the middle. So we can make it much more accessible by doing treatments on and making even the deeper parts active. And here we just ruined it. So that we have still a cheese, but we just make sure that these active sites, they are not anymore there. So, I hope I've convinced you that spectroscopy on catalytic materials is a vibrant field of research, where a lot of things can be learned on catalyst salts. And I hope I also have shown you a flavor where we are going. It's only waiting for the time that we can do real single molecule, single site, and even with a time frame which allows you to see bond breaking, bond making under real reaction conditions. So I think the next generation researchers, I'm sure, will be able to do that. If you've seen that this, what I showed you, is only an evolution of, let's say, 5-8 years of research, where you see where things have been pushed. Last but not least, I would like to thank all the members of my group who have contributed to this work, and of course, thanks to this university for inviting me to be here and to discuss the science which is taking place within our cooperation program. Thanks a lot for being here.
So what I can say after this impressive lecture, honestly speaking, I would say catalyst before was a black forest. Black forest means you don't know what's exactly happening during the reaction. After such kind of spectroscopic techniques, it means you will go through the process. You could understand what's happening, what's the mechanism, how could you control it, how could you activate the catalyst, which material. Please, my students, you have to know that science needs work hard, not to waiting, standing for a short time or to finish your thesis. Thesis needs much more work in order to catch such a kind of work in the future. Thank you for this impressive lecture again. And I would like to invite you tomorrow as well for the young promising scientist as well, Javier. So don't lose this chance in order to listen to the science. Thank you very much.
At the same time?
At the same time, at 11 o'clock. Yeah, of course, sorry.
I'm interested in the nitro thiophenol. You are getting a diazo. What is the mechanism now? You are radiating it with laser,
yes,
silver. What is the mechanism? So, I mean, as an organic chemist, the process is a very long one. It's not like just radiating.
I think it's I invite you to read the art. Actually, one of the referees. See, there's at this moment a dispute on this mechanism. There are two main routes which are proposed, and even the final product is argued is that it's really that product which we make. So I don't have the answer for that. The only thing is we just say, well, there's an argument still in the literature. We don't resolve it. We only make use of this reaction to show that indeed, by irradiating it with green laser light, you can do this photoreduction towards its dimeric compound. And that's it. And more I cannot say. But I agree that this is a much more...
You can scale it up? Or it is only
No. It's really on the nano scale, on a gold nano.
Because if you can, it's a good first chance for painting industry.
Sure.
Yeah?
Other questions? Yes?
You showed so much data on X-ray microscopy, on microcrystals, microcell crystals. Nowadays, everybody is doing nano-cell crystals, like whether they're MTO problems. There's so many literature reports dealing with the application of nanoviewers of this problem, so that they can reduce the chemistry activation. So can you do this X-ray microscopy on nanocrystals?
Yes. Everything what is small enough to put in our reactor and still have sufficient spatial... I mean, our spatial resolution is see, the claim is, X-ray microscopy, this claim is at this moment that something like the spatial resolution is around 9-10 nanometers. The practical resolution, we have to be fair, something like 15-30 nanometers. So every object which has this size, or a little bit larger, you can measure. So yes. And I forgot to show you, but I can maybe later on if you wish. I have other movies where we have been doing on a zeolite crystal, and we map octahedral and tetrahedral aluminum in 3D in a zeolite particle. So it's possible. So I don't see any reason. We also, for example, just to give you an impression what we can do, we can also measure copper zinc metal synthesis catalysis. We did it. Several systems can be studied. So any soft and hard X-ray accessible metal or element, like silicon aluminum, titanium, even nitrogen carbon.
So what about in case if it is not crystalline, semi-crystalline?
No problem.
The marker.
That's fine. You can measure. You don't need, I mean, that's the difference here. You don't need, this is not a diffraction tool. It's an absorption tool. You don't need any crystallinity. Amorphous is fine. So it's, in that respect, very powerful. Or you can also say, yeah, I would like to have also the crystalline phase, yeah. But then you should do micro X-ray diffraction experiments, which you cannot do yet on this scale. I think I have to stop. But it's up to you.
Thank you.
Oh, okay.
Maybe.
Yeah, of course.
With the crystal, you prove that the body orientation is different from the edge. How can you explain that? Why? Is it not the same chemical composition? Is there any difference?
It has all to do with the initiation of crystallization in the initial nucleation process. There's one other area which is still a dispute area, is what is happening during crystallization of these kind of materials. The mechanistic details of crystallization are not yet well understood. That does not answer your question, but what we believe is happening is that we have in the beginning a perfect crystal. And around it, later on, you have, because of the zoning in the ingredients in a material, I mean, in your synthesis vessel, you will have, for example, depletion of certain components. So that means that at a certain moment, this direction will grow faster than the other, or this direction faster than the other. And, for example, there is less or more silicon or aluminum in it, things like that. Then, so it starts to, initially I think it's a perfect crystal, one direction, and later on, these components grow around. That's my explanation. But if you say, do you have proof for that, real experimental proof, that's not there. It's based on yeah, what I show you how the intergrowth is looking, and that you have that middle piece there. Why you have that middle piece in such things? I can only explain that is the initial, the mother crystal, if you can say it, where around it the other components. That's how I explain it. Thank you.
At the end of this lecture, thank you again, Bert M. I would like to invite you tomorrow for the lecture at 11 o'clock, done by Javier. So the title of this talk is Imaging Microscopy, Spectroscopic Methodologies for Studying Individual Cracking of Phase for Catalysis throughout different life stages. Okay? So we have the pleasure to have you here and also Javier. So thank you very much.